So revisiting worksheet 6, they started with, they gave us a motion map here that was quantifiable. So we went ahead and added the positions down below. Remember, this is a position line. Each dot and arrow represents a unit of time. So at 0 seconds, the object was at 1 meter. At 1 second, it was at 3 meters, and so forth. So these 5 symbols represent a total of 4 seconds. Next up, you were asked to write a written description, including starting position, direction, type of motion, and quantify the speed as part of the motion. And with that information, you were then asked to build a position versus time graph and a velocity versus time graph. For the position versus time graph, you then wrote down a specific mathematical model and a general equation for the position versus time graph that we had done prior to today. Next up, we used that slope of 2 meters per second to build a velocity versus time graph. It traveled at 2 meters per second for the entire 4 seconds, so we drew a horizontal line there. At a time later, they asked us shade in the region under this. But on this side, we went ahead and wrote a specific mathematical model for this line on this graph. So to write a specific mathematical model here, the name of the y-axis is velocity, the name of the x-axis is clock reading, the y-intercept was 2 meters per second, and our slope, well, that's a flat line, right? So we put in here the y-axis is velocity, the slope is some 0 value, we don't even know what the units are at this point, and the x-axis was clock reading plus the y-intercept was 2 meters per second. We discussed that since any clock reading times 0 would be 0, that we could say the final velocity is always equal to 2 meters per second, which is what this says anyway, right? No matter what the clock reading is, the velocity was 2 meters per second. And so the general equation we had for this shape of this graph is the final velocity will always be equal to the initial velocity if something is experiencing uniform motion or constant velocity. We were asked to shade in that area and then calculate what that might be. Because the final position was 9 meters and the starting position was 1, we found out the change of position or displacement was 8 meters. They then asked us what the shape was underneath that, the velocity versus time graph. So what was the shape of this thing here? And that's a green rectangle. So when we calculated the area of the rectangle, we did the height times the base. The height of the rectangle actually represents the velocity of 2 meters per second, where the base represents the change in time of 4 seconds. So we went ahead and said that the height is the starting velocity, the base is the change in time, and so the height of 2 meters per second, or the starting velocity of 2 meters per second, times 4 seconds was 8 meters. We recognized that the answers to letter I and letter G are the same. In other words, this 8 meters was equal to this 8 meters here. So we decided that the area under the shaded region of the velocity versus time graph represents the displacement. So next up, we were given a new problem. We were given this data table, position at 0, or at time 0, we're at position 0, and through these clock readings, we had these corresponding positions. So students made a position versus time graph. Looks like we scaled the y-axis by 1s. I think you guys might have had to go by 2s because I think you had 10 boxes down here. Maybe that's not true. Anyway, and we scaled the y-axis by 10s, or by 1s. Next up, we plotted the points and drew best fit lines. Please note that phase 1 I drew with a red best fit line, phase 2 with a black best fit line, phase 3 with a green best fit line, phase 4 with a black best fit line, and phase 5 with a blue best fit line. Notice that the 2 times when it was stopped, I used black, and then phase 1 was red, phase 3 is green, and phase 5 is blue. So we were then asked to build a velocity versus time graph. To do that, we have to calculate the velocities. Well, you guys already know that the velocity is the change in position divided by change in time, but we're specifically looking from 0 to 2 seconds. So we're taking that slope from there. Because it traveled from 0 to 4 meters, and it took 2 seconds to do that. That's 4 meters divided by 2 seconds, 2 meters per second. For the next second, we've got a slope that is 0, right? It's a flat line. So when we punch those numbers in there, we would get, for the velocity from 2 to 3 seconds, change of position was 0 meters in 1 second, so the velocity is 0 meters per second. And then for 3, 4, and 5 phases,
For phase 3, I did an expanded version of the change in position divided by change in time, 10 meters minus 4 meters divided by 5 seconds minus 3 seconds. So that's 6 meters in 2 seconds or 3 meters per second. Phase 4, it was stopped again, so 0 meters over the course of 2 seconds. And for phase 5, it traveled negative 10 meters in 2 seconds, which gave us a slope of negative 5 meters per second. With negative 5 being the largest magnitude of our velocities, we're going to have to scale the axis so 5 fits on here. So we can go up above, we can scale at 1, 2, 3, 4, and 5 meters per second. And down below we'll have negative 1, negative 2, negative 3, negative 4. This would be negative 5 meters per second. So the first phase, which we drew up in red up above, was traveling at 2 meters per second for 2 seconds, and then it was stopped for the next second. And then it traveled at 3 meters per second from 3 to 5 seconds, and it was stopped for the next 2 seconds from 5 to 7 seconds. And then lastly, it traveled at negative 5 meters per second from 7 till 9 seconds. So that's this. Well, they are then going to ask us to find the displacement using these areas. And the area from 1 to 2 seconds would be represented by this red rectangle. The displacement for 3 to 5 seconds would be represented by this green rectangle. And the displacement from 7 to 9 seconds would be represented by the area of this blue rectangle. If you flip over to the next side, here again they ask us to calculate the displacement from 0 to 2. That's that red rectangle that we just talked about. So to do that, we said that displacement is the area of that rectangle, which we said was the initial velocity times the change in time, which is equal to the initial velocity for phase 1 was 2 meters per second for 2 seconds, which equals 4. And how do the units work out here? Well, you have seconds on the top and seconds on the bottom. Meters per second times seconds. So seconds divided by seconds equals 1, so that leaves us with this meters. For phase 2, the logic was stopped. So we still are going to start with the general equation. Displacement is equal to the initial velocity times change in time. So our initial velocity for phase 2 is 0 meters per second times the 1 second it was stopped for. And again, this is for 2 to 3 seconds. Well, I forgot to write down this was 0 to 2 seconds here. So 0 times 1 second is 0. As far as the units go, the seconds reduced to 1, and that leaves us with units of 0 meters. Following that same process, we can find the displacement from 3 to 5 seconds. We can find the displacement from 5 to 7 seconds. And the displacement from 7 to 9 seconds. But next they asked us to find the displacement for the whole time period from the velocity versus time graph. Well, because the displacement for 2 seconds was this, and the displacement for these 2 seconds was this, and the displacement for the last 2 seconds is this, we are going to need to add up the sum of those rectangles. You can put it in the sheet over there if you want. And so we're just going to add up those rectangles. So if we come down here, we'll go ahead and say that the displacement from 0 to 9 seconds will be equal to the total area on the velocity versus time graph. But now we need a formula for that. And this is a little different because we're just going to have to make up something for this. But we want to add the area of the rectangle from 0 to 2 plus the area of the rectangle from 3 to 5 seconds plus the area of the rectangle from 7 to 9 seconds. And the area of our rectangle, let me scroll up here. So our rectangle was 4 meters from the first one, 6 meters from the second one, so we'll go ahead and do that. So for the area for the 2 seconds was represented 2 meters as the displacement.
For phase 3, the displacement was 6 meters. And for phase 3, it would be here. I'm going to go ahead and add, because we said we're adding the areas of these rectangles, plus negative 10 meters. And you guys know that, oh, this is wrong. Meters. So I need to go back. The displacement for the first 2 seconds was actually 4 meters, plus the area of the second rectangle was 6 meters, plus the area of the last rectangle was
Negative 10 meters. Make sure we have those all written.
4 meters plus 6 meters plus negative 10 meters
Is going to equal
0 meters. And that would only work out if the thing,
ended up where it started. Well, take a look back at our data table. We started at 0 meters and we ended at 0 meters.
I'm just now realizing that this has the wrong units right here. This should just say meters on here. Position in meters, not meters per second.
Not sure how that mistake was made, but we started at a position of 0, we ended at a position of 0, and look over here at the position versus time graph. Our starting position was 0, our final position was 0, so our change of position was 0. Last bit, you're going to go ahead and use these data points or your graph to build the motion map. And a pro tip on this one, write down all the position dots first.
So it looks like my screen got moved around a little bit. Go ahead and grab this and push this back to where it belongs. And we're going to start with position at time 0. We were at 0. At 1 second, we're at 2 meters. 2 seconds, we're at 4 meters. At 3 seconds, we're still at 4 meters. At the next clock reading, we were at 7. And then we were at 9. At 5, 6, and 7 seconds. At 8 seconds, we were at a position of 5 meters. And we ended at a position of 0. Now that we've done that, I'm going to add velocity vectors. Normally we make velocity vectors blue, but because we did these phases, I'm going to have the phases match the colors of the previous parts we've done. So I'm going to not run that into the next position dot, but I'm going to make it 1.5 of these hash marks long. And so I can put a single hash mark on those. And then for phase 2, we use green. So we stopped for a second, but phase 3 started at 4 meters. Oh, I didn't put those at 10. At 10, at 10, at 10, and then 5. That's better. Hi, I'm making a video right now, and so for our 5th phase, we're going to have even longer velocity vectors. Looks like I forgot my hash marks on phase 2. Anyway, so that's your motion.
I hope that helps.